Okay, I think we're ready to start again. The next presenters are Hilde Tveit Haaland and Ketil Vågbø from Cegal. They have worked with data science and software development over a long period of time. And both of them are now very focused on how to use and create machine learning tools for the E&P business, both from a developer's point of view and from an end user's point of view. So I'm sharing now with you, Ketil, to present your, or to give your presentation. Go ahead.
Okay, yeah. So yeah, I hope I still have some audience. Sorry about the problems. So what myself and Hilde want to talk about is taking advantage of all the metadata from Geoscience applications to apply that to some seismic interpretation data and use machine learning to do a quality assessment of the interpretation. So the agenda is to first just describe what we mean by geoscience metadata, talk about some of the challenges with that type of data, and then we'll go through a use case where we want to find the best seismic interpretation data from thousands of Petrel projects. We'll go through a solution or a possible solution for doing that, and then we'll go through some demos of browsing the data in Arcgis Power BI, and then we'll have a deep dive into using Python for doing the machine learning. So metadata is actually data that describes other data. So when it comes to seismic interpretation, the interpretation itself, the pics that you do on 2D or 3D seismic, that's the data, and you store that in for example, for 3D interpretation, you store that in a grid data structure. The metadata about that could be what the survey is the data from, what seismic cube was it picked on, who did the picking, what are some of the kind of numerical data describing it with the minimum, maximum values, the density of the interpretation, and so on. And some of the applications that are used for this type of data is Petrel, Decision Space, Geoteric, Paloscan, and lots of others. And all of these applications, they generate this, or the users generate the data using these applications. And typically, these applications can be used in an organization for many years or maybe even decades. And over time, a large amount of this interpretation data with the associated metadata is accumulated into the different application storage solutions. All of this historic data can be valuable. The question is how to take advantage of it. So yeah, here is just an illustration to show, for example, if you use Petrel came out in the early 2000, and if you have been using that for the last 20 years, you can accumulate a lot of Petrel projects. And then if you merge with another oil company, you get a steep, you can maybe double the amount of data that becomes available. So some of the challenges with this type of data is that it's usually not very accessible outside of the application itself. You need to execute the application, or you might need a special API and build custom applications to read this data. For example, with Petrel, you have the Ocean API to access the data with Petrel plugins. And the other providers have similar solutions. But often there's a lack of data management governance for the data. For example, which data version was used for a decision to drill, and if you might have that information when it was actually decided, but after some years, the information is lost. And also because the application might be used differently in different organizations, this can lead to difficulties in consolidating the data. There are user freedom in naming and also coordinate reference systems and units can make it problematic to consolidate all this data. So some of this, what are the solutions for this? First of all, it's try to prevent that the problems arise with having some governance procedures in place, and make sure that end users using the applications are aware of the procedures and what problems can lead to. There are also tools to manage this. For example, we in Cegal have this Blueback project tracker that can help with these problems. But what we want to make this data more easily accessible, and that is to build an index and make it the data searchable, so that you can filter the information and find what you're looking for. So the use case that I want to go through is you have an oil company that has used Petrel for many years. We have several thousand Petrel projects, and there's been mergers between different oil companies, which has led to all this data. So how can we find the best interpretation among all these Petrel projects to, for example, build regional maps or to be used for new prospect evaluations? So some of the problems that we face is that there has been used a lot of different names for seismic horizons, surveys, and cubes. Often there are spelling mistakes in these names so that they can't be exactly matched. There are also many copies of the same data with maybe minor or no differences. And there's a lot of scratch type data with low quality that really doesn't give much value. And there's no kind of tagging, for example, using the Petrel quality attributes for deciding about what's the final data. So the use case workflow we have is to scan all the Petrel projects using the Blueback project tracker tool that we have built, to index all the interpretation data and save that to a SQL Server database. Then we define a naming standard for the main objects, seismic horizons, surveys, and cubes. We map the existing names to this standard name using a fuzzy name matching algorithm. Then the data can be browsed in the web application that we provide, or through map views in Arcgis or Power BI. And on top of that, we can run the machine learning classification to filter low quality interpretations. So this is the setup of the system. We have the Petrel projects, the Blueback project tracker tool. We index all the data, save it to a SQL Server database, and then we can access it with the Python and the other tools. So this is a list of all the metadata that we save for the interpretation data. And some of this is more descriptive type metadata, but we also have some derived numerical attributes. For example, the defined number of points, the point density, the compactness, and location of the data. Here's an example of the naming problems with the naming. So we have all these variants of the name Oscar, and we map it to a standard name using this fuzzy name matching algorithm that I talked about. And similarly for a seismic survey name, different names used in Pachel, we map it to this single name. So that makes it much more possible to search and filter the information later on. So what I'll do now is show you some of how this can look in ArcGIS and Power BI, and we'll head over to the Python demo. So let's see. Do you now see the ArcGIS application? Hopefully. So what we have done here is import the information from the SQL Server database into a map, so the interpretation data becomes available. And also we have a table view of some of the metadata down here. So if I can zoom in and I can click on an object in the map, and I can see the interpretation data. And also here we are using then the mapped names for that. Also, we export images for the interpretation, so I can position the images of the interpretation in the map. So that's using ArcGIS. I can also show this information in Power BI. And here you see I have a map plugin into the Power BI report. I can then filter using these standard set of names, and I can the map is zoomed to where that position is, and I can look at the an image of the interpretation data here. So that was quickly the Power BI and map presentation. So Hilde, are you ready to do the Python part of the presentation?
Hi everyone, my name is Hilde Haaland. I'm a senior geophysicist / data scientist working with Cegal, and I'll just demo quickly the machine learning part of trying to use this data that Ketil has extracted and organized in this database to be able to classify what's good and what's bad data. I think I'll just turn my camera off again just for the purpose of having a good view of the screen. So I don't have any slides, so I'll be showing you kind of the code as it is running in Jupyter Notebooks, and also some dashboarding solutions that I've set up kind of from these notebooks. So as Ketil talked about, we've scanned these databases and created the SQL database with all of this data available, and Ketil has then accessed it through different tools such as Power BI and ArcGIS. And then the next step of what we want to use this extracted interpretation data for is to take a small subset of that data, classify what we believe is good data and what we believe is bad data manually, and then from that create the machine learning classifier that we can then apply to all of the rest of this data available in this database, so that we can have a measure of, or at least an indication of what is good and what is bad data in our data set without having to go through a vast amount of data, say for example after a merger, or after consolidation of companies, or just an extended period of time. So we decided to use Python for this part of the workflow, and the code was actually written in using Jupyter Notebooks. So in that way we can kind of use the same IDE setup both for creating an interface to do this manual interpretation of good and bad labels to surfaces, and also apply the classification and evaluate it kind of within the same environment. So the steps that needs to be performed when we want to then kind of go from a database of surfaces to a database of surfaces classified as good or bad is that we need to create this training data set. And to do that, we need to connect to the database so that we can retrieve data and then write back data. So let's jump to that. We won't go through the code in detail here, so don't worry too much. I'll just go quickly through the steps there. So we connect to the database, and then we define some functions. Very simple functions just to retrieve data and write data back to the SQL database that Kettle has set up. And we have some nifty kind of Python tools to connect and query databases. So we've used PyODBC, which is a Python database connector. And then we built this very simple interface to be able to just kind of click through data and classify a surface as good or bad. And the beauty with kind of using a notebook setup like this is that you have many plotting tools available to you. You have like Sebastian showed in his talk as well. You have a very nice widget library called IPyWidgets that's native to Jupyter Notebooks, which makes it very quick and easy to kind of create button controls in your notebook. So we've used kind of a combination of plotting and IPyWidgets to create just a very simple interpretation interface. And if we jump to that, so with all the code kind of running above here, we jump down here. So we created a a classification interface. And then in addition to kind of having this in a notebook, I'm actually using another built-in Jupyter tool called Voila. So we'll just jump to that. It creates basically a dashboard of a notebook. So I'll just jump to that so we can kind of see. So from the code in that notebook that we showed, or that I showed, this is basically what we're left with. This is an interface where I've collected then some surfaces from my database. And then I've collected the metadata that Kettle referenced in this talk in a table here. And then the combination of the image of the surface and the information here in this the table will allow me to kind of define whether or not I think this is a good surface. So to kind of build a good classifier, you need a good amount of training data. So depending on kind of the size of your database, you should, I mean, if you have a very large database, you know, you might not need more than 5%, 10% of data to build an okay classifier, if that data is representable of most of your data in the database. In this example, we don't have that much data in this demo database, so I'm probably interpreting not enough data to build a good classifier, but at least it's a demo of how you would then kind of step through it and classify enough. So in this interface, I have the option of giving a surface a classification of good or bad. I can click, go to the next horizon if I've decided on the classification, or as you see here, these have actually been classified previously because I have a current classification when I picked this up from my database. But then if I want to change this, I can click good. I'll just click next horizon, just update it, and I'll go back, and then I'll see previously classified as good. We'll set that back to bad. And then I can use the drop down list here to kind of go to whatever surface I want, and then classify it to define my data set. So once I've defined kind of enough surfaces as good or bad, I'd like to build a classifier from this. So now I have kind of some truth data where I have, you know, a set of surfaces with metadata attached to it, and then a definition of whether or not this is good or bad. So I'll take that data and I'll use it as input to building a classifier. And when we built a classifier for this project, we tested a lot of different classifiers, and there are probably many other options than using kind of what we ended up with, gradient boosting classifier from scikit-learn. But that's what we're going to use in this example. So the way we then kind of train or create the classifier is that you initiate an instance of this classifier from scikit-learn, and then you train that classifier basically just by inputting the data that we've then manually labeled as good or bad in a specific format, so that the classifier that we're kind of just implementing builds a relationship between that input data and that manually labeled good or bad classification that I've given to the data set. And once we've done that, I basically just save out that trained classifier to a file. So we use something called a pickle, which is a way to save a Python object with a state, basically. So instead of just saving out a piece of code, I'm saving out kind of a Python object that has been trained on something and kind of has a state. We won't go through this in detail, just in the interest of time as well. So once we've then created that classifier in this build classifier function, sorry, I would like to apply that to my data. So when I built the classifier, I only used the data where I had done this manual good-bad interpretation. Now I want to apply the relationship in that classifier to all of the data in my database. So not just the data that has a manual interpretation, but I mean, the purpose of this is to then be able to extend that relationship that I've defined myself from this manual interpretation to all of the data that I don't have time or don't want to spend time manually classifying as good or bad. So I read all the data from my database. I read my pickled model from file. I apply my pickled model to all of the data, and then I write it back to my database. So fairly simple. I've just taken this database that Catalyst made and then updated a column in that database based on some manually interpreted data that I've built a classifier from. And then you can kind of say, okay, that's cool. I've added a classification to my data. I can go in and I can look at like individual surfaces and say, oh, okay, that was predicted to be a good surface. It looks okay. Or that was predicted to be a bad surface, but I think it looks good. So you're kind of like, it would be nice to have a mesh or an overview of kind of how well your classifier has actually performed.
It looks like your screen is frozen.
My screen is frozen.
Yeah. Oh, here it works. No, here it goes. Yep. Now we're back.
Okay.
Yep. Now we're on the right one. Yep.
Good. Yeah. So I can use different tools available to me to evaluate how well my classifier has performed. So there are kind of easy ways of doing this, just looking at what features kind of drive the interpretation. And there are some more, let's say, advanced tools that are freely available, open source tools that we can use to easily get an overview of how our classifier performs. So I'll just do this very quickly because I see we're running out of time here. But if we want to evaluate this gradient boosting classifier that we built, I'll just connect to my database again and retrieve some data. And then you can see in this example that we're running, I have 500 points in my data set, and I've manually interpreted 62 points. So it might not be the best representation of this data set. Should probably have interpreted more, but still, it's an example. And then if we go down and look at kind of the distribution of manual interpretation and predicted, manual classification and then predicted classification, you can see that for my manual label distribution, I have about 13% band. And then for my predicted label distribution, I have 42% band. that could indicate that I have some class imbalance maybe in my data set, or potentially that the data set or part of the data set that I've manually interpreted was not kind of very representative. Or it could be that I did have more bad surfaces in the rest of the population. But to kind of dig a bit more into that, we have tools to use. So I'm going to use an open source tool called Ash, which is a dashboard tool that basically just loads the classifier that you've built, and then allows you to kind of understand a bit more why the classifier behaves as it does. So this is a finished built dashboard. I've basically just implemented it and then loaded my model into it. And here I have some feature importance. So I can see I built my classifier using 6 features, so 6 pieces of information from this metadata collection. And then I can see that defined area and point density together are the ones that kind of mostly drive the classification of a point. I can also step in to each specific point in my data set. And then I can see I'm now looking at the classification score 1, so a good surface. And then I can see for this first data set, or sorry, data point, I can look at the local explanation to see kind of how the different features contributed to a classification. And I can see, if I go over to this plot here, I can see the feature contribution for each of these points plotted on a scatter plot. So yeah, this is actually ID0. That was that was lucky. So I can see that for defined area, the contribution is 14 point, yeah, almost 15 for a positive, sorry, a 1 classification, so a good surface classification that corresponds to this number here. I can step through, you know, different points there. I can look at a poor classification, and you can see that the local explanation here skews to the negative. So I'm having more kind of contribution towards a bad classification than the positive classification. So these tools then let me kind of understand a bit more what's going on in my classification. So if I see results that I either don't trust or that I don't know kind of how I got to, I can use tools like this to kind of step through my classifier and then discover problems or gain confidence in the performance of my classifier. That's really what I had to show. I don't know if we have time to go back to you, Ketil.
Yes.
1 minute.
We have 1 minute.
So I can.
Let's see if I can manage to show. Do I show the? Do you see my screen now?
Yes, we do.
Okay, fantastic. I've learned. So yeah, so the thing that Hilde presented. Now I'm back into our tracker application. So the prediction from the machine learning algorithm was saved back to the database, and now I can see that here is showing the interpretation data, and I can see the prediction. So this first one is predicted as bad, has the value 0. So if I look at the image for that interpretation, it looks like this. So that looks bad to me. But then if I look at one that's classified as good, we can look at this one. That looks better. So that's how this then can be used. And then just to round off this, the last slide is really just to say that, okay, this what we have shown is part of the next release of the Blueback project tracker, and that is expected to be released now in April. So thank you for your attention, and back to you, Stoffe.
Thank you very much for a very interesting discussion on how to evaluate data and quantify data.